Hello. So now what we're going to do is we're going to graph this polynomial. Okay. And so I have a list of certain things that we're going to talk about. Okay. As we graph this polynomial. And the first thing we're going to talk about is the domain. Okay. For any polynomial, the domain will always be from negative infinity to infinity. Okay. And just so you remember, the domain is the set of x values that the expression defined in the polynomial can be calculated at. When you take the square root, for example, which is not a polynomial, but you cannot take the square root of a negative number and get a real number. So we remove negative numbers from the domain of square root functions when looked at as real functions from real numbers to real numbers, right? But there are no such restrictions on polynomials like this. Okay? Now, we're not going to talk about the range yet until the very end. Okay? And we will see that with respect to the algebra level, there may be cases when we won't necessarily be able to get the range using purely algebraic techniques. Okay? And so we're going to leave that one for the end in this particular example. Okay. Now, in this particular example, the next thing we're going to do is we're going to find the X-intercepts. Okay. Okay. So, what does it mean, or how do we find the X-intercepts? First of all, what does it mean, an X-intercept? It means a point or points on the x-axis through which the function's graph crosses. We know that every point on the x-axis is a point with y-coordinate 0. And so that leads us to the idea behind how we find the x-intercepts. Okay? So if every point on the x-axis has y-coordinate 0, then to find any point on the graph of this function that is on the x-axis, or to say it differently, to find the x-intercepts of f of x, we set the f of x equal to 0 and solve for x. Okay? In this case, I'm going to set this expression equal to 0 and I'm going to solve for x. Okay? Right, I want to find any and all real numbers x that make this equation true. As in the case of quadratics, if I find imaginary solutions to the equation, then those correspond to zeros of the equation, values of x that make the equation 0, but they do not correspond to x-intercepts. Okay. Now, here also we begin to see the deviation between the quadratic cases and the quadratic case and the linear case that came before. In the past we would graph lines in quadratics, and we had a technique that we could use all the time for either of these to get the roots in a systematic fashion. In the linear case, which is the simplest polynomial, we just solve for the x. In the quadratic case, we use the quadratic formula. We know that applies to all quadratics. In the general polynomial case, we have a hodgepodge of techniques and the rational root theorem, and of course, more generally, we have the intermediate value theorem to estimate roots if we can't find them using our kit bag of techniques that we've assembled. Again, the kit bag for polynomials is this: rational roots theorem, factoring by grouping, certain polynomials that come out as common as special factors like sum of cubes, these kind of like special cases, and of course polynomials that have some certain structure that let them be factored very easy, such as if the polynomial is in a quadratic form, things like this. And again, as I mentioned, the rational roots theorem. And beyond that, if it's not possible to factor it like that, then we have to estimate the roots. Okay, but fortunately, if you look at this carefully, you will see that this polynomial factors by grouping. Look what happens here. If I pull out an x squared out of this first term, I get out of these first two terms, rather, let me say that. x squared times what gives me this? X squared times x minus 3. Now look at this. Isn't it interesting that if I were to take negative 4 and I were to multiply it times negative 3, I would get positive 12? So I'm going to pull out a negative 4 out of the final two terms, and I get, aha, negative 4 times x gives me negative 4x. Negative 4 times negative 3 would give me positive 12. And look, let me walk you through this again. So here I have, so for these two terms, I pulled out an x squared. X squared times x, that's x cubed. X squared times negative 3, that's minus 3x squared. Negative 4 times x, that's negative 4x. And negative 4 times negative 3 is positive 12. So we can see that this expression is the same as this expression. But so here we have seen that this polynomial can be factored by grouping into this form. Now, since I have this term common to both of these terms, I can factor it out, okay? And so, like, I can factor it out this way. So I have x minus 3 times x squared minus 4, right? Notice how the x squared minus 4 comes from there, okay? And that equals 0. Now look at this term here. Do you recognize this term? Does this look important? It looks important, right? I don't know if you guys remember, there's a special formula. X squared minus y squared equals to x plus y times x minus y, okay? What is that? That's the difference of squares. I know that 4 is 2 squared. So then this finally can be written as x minus 3 times x plus 2 times x minus 2, okay? And that equals to 0, okay? So now this is a very nice example because we're able to apply these factoring techniques that we know for this polynomial, okay? And we're able to get a fully factored case, okay? Now, before we proceed, I want to make a point about what happened here. What we noticed is that I took this expression on the left, and I was able to rewrite it as this expression on the left, okay? So before we solve this for the zeros, I want to state that in this particular case, we were able to write this polynomial in factored form as x minus 3, x plus 2, x minus 2, okay? Okay. And so now we're ready to get the zeros, okay? So I know most of you might be familiar with the zero product property, and the way you might be familiar with it is if I have two numbers being multiplied to give me 0, if I have two real numbers being multiplied to give me 0, then either the first one is 0, the second one is 0, or both is 0. But we can state it more generally as follows. So we can state it more generally as possible. If several real numbers are multiplied and their product is found to be 0, then at least one of them is 0, okay? So in this particular case, I either have x minus 3 equals 0, or I have x plus 2 equals 0, or I have x minus 2 equals 0, okay? Because if the product, because remember, for any x value, x minus 3 will be a number, x plus 2 will be a number, x minus 2 will be a number. So if I'm forcing those three numbers to multiply to give me 0, then one of these has to be 0. Either this one is 0, this one is 0, or that one is 0. This one, right, yeah, so this one, if this one is 0, look what I do. I can add 3 to both sides here, and I get x equal to 3. What about this one? Minus 2, x equals to negative 2. This one, plus 2, and I get x equal to positive 2. Okay, so we have found our x-intercepts, okay? And let me make a little notation of that here. Our x-intercepts here are 3, 2, and -2. Okay? And now here I'm going to make a little table here of their multiplicities. Okay? Because that's going to play an important role in how this graph is actually going to look on the paper. Okay? So whenever it's possible to get the factorization of the polynomial as it was possible here, for example, we saw that it was this factorization. We saw that it came from our process. We got this expression on the left hand side of our sorry about that, I was stuttering a little bit there. As we performed the factorization of this left hand side, we arrived at this expression, and we saw that since we didn't divide out and cancel any common multiple, we could see that this factorization is identical to this factorization. Okay? In other words, if you multiply this left hand side out, you will get this left hand side, and that left hand side of this equation is identical to the defining expression for this polynomial, and so this expression on the left hand side must also be equal to this polynomial by that argument, and therefore this is a factorization of that polynomial. Okay? Having made that factorization, I want you to observe how each of these factors is written to the first power. Okay? What do I mean by that? Okay, let's erase this temporarily. Okay? Okay. So here I have f of x equals x minus 3 times x plus 2 times x minus 2. Okay? Now, if the factorization of a polynomial has a factor, but I don't write a number explicitly, that's just shorthand for this. Okay? That's just shorthand for the exponent of those to be 1. Okay? I want you to remember that whenever we write, like, for example, x, okay, this is just a shorthand for 1 times x to the first power. In the same way, if I just write this expression like this in the factorization, I'm really writing that expression raised to the first power. Okay? And so, now you might ask, okay, David, why are we talking about this? We're talking about this because the behavior of the graph of the function near a zero will be, or at a zero, will be determined by its multiplicity. If the multiplicity of that zero is odd, the multiplicity being the degree associated to that factor in the polynomial, if the multiplicity of that factor is odd, then the zero corresponding to that factor will be a location where the graph crosses. And if the degree of the polynomial, if the multiplicity of that factor is even, then the zero associated with that factor will be a place where the graph bounces or touches. Okay? In this case, you can see that each of these factors is to the first power. 1 is an odd number. So we can see that in the particular case of this polynomial, the graph will cross at each of these zeros. Okay? It will not bounce at any of them. Okay? Now, just for discussion's sake, if instead the factorization had been this, okay, let's say x minus 1 squared x plus 2 to the first, like this, then the zero associated with this first factor, namely 1, how do I know that? Because if I plug in 1, 1 minus 1 is 0. So the zero associated with this first factor would have multiplicity 2, and so if I were to plot this graph, it would bounce there at 1. Now, we don't know if it's bouncing from the top like this or if it's bouncing from the bottom like that. We're going to look at that later when we talk about the end behavior and stuff. Okay? And in fact, let me photograph this so I can do this as an example in a moment. and of course, so in any case, I think you all can see what I'm saying, all right? So in this case, we have our x-intercepts, and their multiplicities in this case are just 1, 1, and 1. And I recommend you always make a little table like this when you're listing your x-intercepts on your paper, okay? So now it's a good time. Usually you might say, David, we could move straight to the calculation of the y-intercept, right? But I want to go straight to the end behavior, okay? And the reason for that is because before we go to the end of this problem and get the final graph, I want us to get to draw a simple cartoon that may, in some cases, be all we need, okay? So here I have summarized. This is the so-called leading coefficient test, okay? This is the leading coefficient test, okay? And the purpose of the leading coefficient test is to let us find the end behavior of a polynomial, okay? So I'm going to copy our polynomial here for our purposes. F of x equals x cubed minus 3x squared minus 4x plus 12, okay? And what I want you to observe here is that, let's read the leading coefficient test together, okay? Let f of x be a polynomial. What polynomial? F of x equals a sub n x to the nth power plus a sub n minus 1 x to the n minus 1 power plus dot 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 plus a1x plus a naught, okay? And so then the test says that if n is even, what is n? Notice how in the way I wrote the polynomial, it's in terms of decreasing power. What do I mean by that? Or in decreasing degree. That means that the an, x to the n, is the term of the polynomial that has the greatest degree. Okay, and that's in fact called the leading term, and the a sub n is known as the leading coefficient. Okay, and that's why this is called the leading coefficient test. Okay, let me write this down here. Here, a n x n is leading term, and a n is leading coefficient. Oh my God, I'm sorry that this is so like bunched in here. Okay. But so then if n is even, what is that saying? If the degree of the polynomial is even, and if the leading coefficient is positive, then we will see it'll go up to the left and up to the right. Okay, that wasn't me dancing, by the way. Okay. Then, but if the leading coefficient is negative, then it'll be down to the left. Down to the left and down to the right. Okay. Now, on the other hand, if n is odd, and if a to the n is positive, then it'll go down to the left and up to the right. And if the a sub n is negative, it'll go up to the left and down to the right. Okay. So in this case, I ask myself, what is the leading term? I look at my polynomial, which in this case is going in terms of decreasing degrees. So I know that this term has the maximum power. And the reason why I made the point of mentioning it this way is because it is possible that your instructor may decide to jumble these polynomials to test whether you guys are paying attention or not. In any case, here we have the leading term, which in our case is just x cubed. Okay, and whenever we have a term like this, we can see in our brains that this is a shorthand for, so x cubed is shorthand for 1 times x cubed. Okay, whenever you have, whenever in a polynomial you have some expression like in x and it doesn't have a number in front, it doesn't have a coefficient written in front, that's just shorthand for 1 times that term. And so that means that our leading coefficient, in our case here, is positive 1, okay? So now we can test. Look at the degree here. So the degree here is 3. Okay? So is the n even or is the n odd? It's not even, right? The n is 3. Okay? No, the degree is 3. So n must be odd. Now, is the an positive or is it negative? 1, positive or negative? It's obviously positive, right? So here, the an is positive. So I know that the graph is going to go down to the left somehow and up to the right somehow. Okay? Okay. So now we're actually starting to begin to see enough where we can kind of graph this, okay? Like this. Now, I want to make a brief note here. There are other ways of writing the end behavior, but we're going to use this because it'll be good for us, okay? Later on, in another example, I may use the so-called limit notation to describe it, but that's more complicated to understand. So we're going to go with the simple pictorial way, okay? But so now, what I want to show you is how we can use this and the fact that we already got the x-intercepts to kind of draw a cartoon of the graph. What do I mean by a cartoon? What I'm saying is a picture that captures a lot of the information of the graph that might be of interest to us, but without going all the way to the end and getting all the details, okay? Sometimes this is good enough. So for example, from the fact that I have the x-intercepts and I have all their multiplicities and I know they cross everywhere and I know the end behavior, then if I imagine that I draw the x-axis like this, okay, then I know, let's say this is -2, over here this is 2, over here this is 3, let's say. I know it crosses as each. Why? I know that the graph of f crosses at each of these x-intercepts because each of these x-intercepts we saw had odd multiplicity, in particular multiplicity 1. And now because we know the end behavior is down and to the right, so somehow it's going to go up this way. Somehow it's going to go down this way when we're beyond these locations. So my cartoon is going to have to look like this. You see? It's going to have to cross here. It's going to have since it has to go down this way to the left, then that means that when it crosses here, it's crossing in here like this. Then it can't cross the x-axis again until it hits 2. So this mound has to go higher, and then it finally crosses at 2. But then it has to cross through 3 very rapidly, and it has to, and because the end behavior is like that, we can draw this cartoon. Now you might say, David, okay, we're learning how to graph this function. Why would you stop and make a cartoon like this? Or what's the benefit of this? Let me show you. We know that, for example, if I have this graph of f of x, the f of x corresponds to the y of the graph, how high it is from the y-axis, from the x-axis, or how low it is from the x-axis, depending on whether the f of x turns out to be positive at that value of x or negative at that value of x. If I wanted to find out, in this particular example, if f of x, or where f of x was greater than 0, okay, then what would end up happening is that I could draw this cartoon and I could say, aha, look, the f of x is positive here because the graph is above the x-axis. And it's also positive here because it's above the x-axis, right? And so here, with just this cartoon, we don't need all the rest of the detail. With just this cartoon, I already know that f of x will be positive on the region from -2 to 2, union from 3 to infinity. Because the 3 to infinity, you see that piece has to go up. It has to go up forever. And that's because of the end behavior says it's going to go up forever on that side. And because we know that there is no root, there's no x-intercept to the right of this, okay? Okay. Anyway, now that we've drawn that cartoon and we've looked at the graph, we can also address another, not the graph, but the cartoon of the graph. We can also address the question of turning points. For a graph of degree n, the maximum number of possible turning points is n minus 1. Okay, so here we have a quadratic, we have a cubic. It's a third degree polynomial. The maximum number of turning points it can have is 2. And so here we can see it turns 1 and it turns 2. In this case, we actually do have 2 turning points as well. Okay. And so that's an important guideline also, okay? So whenever you have a cubic, you know it can't turn 3 times, okay? It has to turn 1 less, okay? Okay. So remember, the maximum possible number of turning points for a polynomial of degree n is n minus 1, but that is not to say that there will actually be n minus 1 turning points. And the reason why I did this after the x-intercepts, after we draw this cartoon, is because it was only at this point that we had enough information about the graph to figure out how many actual turning points there were. Okay? Yes. And so now finally we're going to talk about the y-intercept, and we're gonna draw the actual graph. Well, actually, before we move on, I want to point out something else. Notice how for the odd degree polynomials, since it's going to go down forever on the left and up forever on the right, or up forever on the left and down forever on the right, in any case, I know that the range of an odd polynomial will always be from negative infinity to infinity. But for the even polynomials, that is the situation where to get the range will require calculus. Okay. Well, to get the range by hand will require calculus. Okay. But in any case, now that we've done everything that we've done, all this preparatory work, we're going to find the y-intercept, and then we're going to do the formal graph. Okay. So let's do that. So now we're going to find the y-intercept. Okay. So how do we do that? To find the y-intercept, we set the x equal to 0 and solve for y. We have our polynomial, so we can plug in. F of 0, okay, is going to equal to 0 cubed minus 3 times 0 squared minus 4 times 0 plus 12, okay? 0 times 0 times 0, that's 0. 0 times 0, 0. Times 3, 0. 4 times 0, 0. So all this expression here becomes 0. So we end up having 0 plus 12. Aha. It crosses the y-intercept at 12. Okay. And so now finally we can draw our formal graph. Okay. So one of the things I also want to point out to you is the following. Whenever you're drawing a graph like this, you know, you want to look at what x's you need to draw in your picture. Here we already saw that the x-intercepts were at negative 2, 2, and 3. So we don't have to draw like an x, we don't have to draw from negative 10 to 10 on our x-axis. We only have to draw maybe from negative 3 to like 5 to see the main part of this graph. Now I want to put a quick caveat in there. What I'm doing right now is kind of drawing the textbook version of the graph, okay? Which is of course what you guys, what I want you guys to see right now. However, what's important to know is this. In the real life situation, when you get a graph, when you're getting a function to graph or something, you might want to graph it in a particular region of x that's of interest to you because it's part of the problem you're working on, whatever. In those cases, you'll plot that part of the graph, okay? And so it will deviate from this in the sense that maybe you're not going to want to plot certain parts here. You might want to focus in on this other region. It might be totally outside of this region of x. It might be totally outside of the region that we're going to graph, but that's okay. Okay. Here we want to look at the main landmarks of the graph, how it behaves near those landmarks, for example, the x-intercept, the y-intercept, and how to get a good visual picture of the graph's behavior, okay, to develop intuition and insight. Okay. So now let us proceed. So right now I'm going to do the calculations of a table which are going to aid us in the graphing of this function. Okay. So by making a table, what I'm going to do is I'm going to try to figure out among the part of the graph that we draw, I want to get a better idea of how it's going to look. And in algebra, what we can do is like there are certain things we can evaluate. As we saw, the multiplicity of a root tells us whether it bounces, the graph bounces at that intercept, or whether it crosses. We can see where it crosses the y-axis using the y-intercept. We can see how the end behavior is from the leading coefficient test. But like how high the graph goes and stuff like that, we're going to learn how to do that in calculus later on. But so for our purposes, what we can do to get an idea, a feel for that, is by plotting a few points. Okay, so we mentioned that we're going to be plotting x's near this region. Okay, so I know, like, if I put -2 here, I know that's 0 because it's one of my x-intercepts. So I want to plug in -1. I want to plug in 0, 1, 2. Now 2 is another x-intercept, so that means the y for 2 is 0. And I also know that at 3, it's 0. So maybe I want to plug in 2.5 as well here to see what's going to happen in between, to get a feel for what's happening. And then a little bit beforehand, maybe -3. And then here, I'm going to figure out what the f of x is. And then, let me see, and maybe we'll plug in 4. So now, let's fill in this table to get an idea of what the points are going to look like. Let's start with -3. What is f of -3? F of -3 is -3 cubed minus 3 times -3 squared minus 4 times -3 plus 12. Okay. Okay. So now, what does -3 cubed mean? That means -3 times -3 times -3. -3 times -3 is +9. Times -3 again is -27. Here, -3 squared. -3 times -3, that's +9. Times -3, we're going to be -27. Okay? -4 times -3, I'm going to be plusing 12, and then plus 12. Okay? So now, -27 minus 27, that's going to be -54. Then I bring down the plus 12 and the plus 12. What's -54 plus 12? That's -42. And then I bring down the plus 12. Okay? And then, so, you might say, David, how did you get -27 minus 27 is -54? Well, what I can do is I can say -27 minus 27 is, by definition, -27 plus -27. And when we have when we're adding two numbers with the same sign, be that sign positive or negative, we add the absolute values of those numbers. So in other words, 27 plus 27. And we keep the common sign they have together. In this case, it's a minus plus a minus. So it'll become minus, and then 27 plus 27, that's the 54. So that's how I was able to get that to that. And then how did -54 plus 12 become -42? Okay. So the way that happened was as follows. I know that -54 plus 12, here I'm adding two numbers of different sign. Okay. So what I'm going to think in my brain is this. Of these two numbers, which has the bigger absolute value? The absolute value of -54 is 54. The absolute value of 12 is 12. Which one has the bigger absolute value? The negative one, right? So my result is going to be negative. Then, how do I get the value? I subtract the absolute values, where I subtract the smaller absolute value from the larger absolute value. Here, in other words, it'll be 54 minus 12. 4 minus 2 is 2. 5 minus 1 is 4. Okay? And that's how I got the, and so the sign came from the fact that this one had the larger absolute value, and it being the negative. So it'll be negative, and then the value is 42. So that's how I got the -42. Following the same procedure here, I can see that I'll get -30 here. So my value at -3 is -30. Okay? What about at -1? By the way, I know that sometimes it can be a little bit tedious to do these calculations, but by doing them, you can have a better confidence in your graph. By the way, I forgot to mention, at x equals 0, what happens? That's the y-intercept, right? We already know that the y-intercept is 12. So that's one less thing we have to calculate, okay? What about f of negative 1? F of negative 1 is equal to negative 1 cubed minus 3 times negative 1 squared minus 4 times negative 1 and then plus 12. So I begin by asking myself, what is negative 1 cubed? That's negative 1 times negative 1, which is positive 1, times negative 1 again, which is negative 1. Okay? Just to be clear, I know that can be a little bit confusing. What's negative 1 cubed? That's going to be, by definition, 3 copies of negative 1 being multiplied together. So it's negative 1 times negative 1 times negative 1. A negative times a negative is a positive, so these two first ones become positive 1, and I have to still multiply them by this third negative 1. A positive times a negative is a negative, and 1 times 1 is 1, so it's negative 1. Okay, so that's how I got that, in case you wanted to see that in full detail. And then, so now, what about this? Negative 1 squared, that's positive 1, right? Because a negative 1 squared is the same thing as negative 1 times negative 1. And a negative times negative is a positive. 1 times 1 is 1, so that's positive 1. So negative 3 times positive 1 stays negative 3. Then I'm subtracting 4 times negative 1. Or in other words, I'm subtracting negative 4, which becomes adding 4, right? Okay. And then I add 12, like this. Okay. Okay. And then here I can start combining. What's negative 3 minus 3? That's negative 4. And I bring down the rest of this. Plus 4 plus 12. Now you might say to me, David, how is it that negative 1 minus 3 is negative 4? Again, negative 1 minus 3 is equal to negative 1 plus the opposite of 3. And since we're adding two numbers with the same sign, we keep the sign, so it'll be negative, and we add the absolute values. 1 plus 3 will be 4. Okay. Okay. Now here, I have negative 4 plus 4. This is going to combine, and it's going to give me 0. And then I bring down my plus 12. And then what's 0 plus 12? That's just 12, like this. So that's what goes here. Okay? Okay. So now, we can calculate what is f of 1 to get this value. F of 1 is going to be 1 cubed minus 3 times 1 squared minus 4 times 1 plus 12. What is 1 cubed? 1 times 1 times 1. What's 1 times 1 times 1? It's 1. What's 1 squared? It's just 1. So minus 3 times 1. Well, 3 times 1 is 1, so it's minus 3. Okay? What's 4 times 1? 4. Minus 4? Minus 4, right? And then plus 12. Like this. 1 minus 3, that's negative 2. And then I bring down my minus 4 plus 12. Okay? What's negative 2 minus 4? That's negative 6. And then I bring down my plus 12. Then, what is negative 6 plus 12? That's positive 6. So that's what goes here. Then here, we're in position to calculate the f value at 2.5. Now, I can write 2.5 as a fraction by expressing it as, let me see here, as 5 over 2. Okay? Let me see here. 2.5. Okay. Let me see here. So yes, now you might say, okay, David, how could I express 2.5 as a fraction, right? Here's how I do it. I remember that this corresponds to the 10th place, right? Right? So in other words, I can see this as 2 plus 5 over 10. Okay? Because it's 2 plus the 0.5. And I saw that the 5 is in the 10th place, so it's 2 plus 5 tenths. Now this fraction simplifies to 2 plus, if I divide the top and bottom by 5, I get 5 divided by 5 is 1, 10 divided by 5 is 2, so I get 2 plus 1/2. Then I ask myself, can I add these? Not quite. Why not? Because the 2 is not yet a fraction. I can make it a fraction by setting it as the numerator and 1 as the denominator, and then I add the 1/2 to that like this. So now the question becomes, can I add them yet? And the answer, unfortunately, is no. And why not? Because they don't have the same denominator. So what I'm going to do is I'm going to multiply this first fraction times something plus the second fraction times something with the intention of having these products be fractions with the same denominator. Okay? If I ask myself, if I look at 1 and I look at 2 and I ask, is there a multiple of 1 and a multiple of 2 that is common to both? In this case, I know that 1 times 2 is 2. 2 times 1 is 2. So 2 itself is a common multiple of 1 and 2. So here, I'm going to multiply this one by 2 on the bottom and on the top, and this one by 1 on the bottom and 1 on the top. Because when I do that, first of all, any fraction with the same numerator and denominator is numerically 1. What does that mean? That means that just like 1 times 3 is 3, this fraction times this fraction will give the same number. But as a fraction, it'll just look different. Okay? In this case, it'll be 2 times 2, which is 4, 1 times 2, which is 2, plus 1 times 1 is 1, and 2 times 1 is 2. What I mean by it'll look different is this. You can see that 4 over 2 is still 2. 4 divided by 2 is 2. But it looks different than 2, because you see it looks like a fraction. But the key thing here now is that because there are two fractions with the same denominator, I can combine them. What's 4 plus 1? 5. So when I add two fractions with the same denominator, I add the numerators and keep the denominator. So this is 5 over 2. Right? So I'm going to think of 2 over 5 as 5 over 2 when I do the calculation. Okay, let's do this together. Okay, stand by, please. So now, let us evaluate the function at 5 halves. Okay? Sorry about that. Okay. So what I'm going to do is I'm going to do this. Watch this. So f of 5 halves is equal to 5 halves cubed minus 3 times 5 halves squared minus 4 times 5 halves plus 12. Okay? Now, down here, you can already tell I'm going to need to know what 5 halves squared is and what 5 halves cubed is. Well, 5 halves squared is going to be 5 halves times 5 halves, right? Because how do we read this? We read this as 2 copies of 5 halves being multiplied together, which is what I have here. When I multiply two fractions, I multiply the numerators to get the numerator of the product, and I multiply the denominators to get the denominator of the product. 5 times 5 is 25. 2 times 2 is 4. And so I see that 5 halves squared is 25 over 4. What about 5 halves cubed? This is going to be 3 copies of 5 halves multiplied together, like this. Okay? So, but I already know that these two will multiply to give me 25 over 4. And then I'm going to multiply it by 5 halves. Again. 25 times 5, that's 125. And 2 times 4 is 8. Like this. So now I can start to rewrite this. Oh, and let me also, okay, I'll wait until the next step. So this, I can now rewrite it as 125 over 8 minus 3 times 25 over 4 minus 4 times, 5 halves plus 12, okay? Now you can see that in this case and this case, there's a coefficient in front. But I want to make it a fraction so it'll be easier for me to multiply. So I'm going to see this as 125 over 8 minus 3 over 1 times 25 over 4, right? Because I can rewrite any whole number as a fraction by setting it over 1. Minus 4 over 1 times 5 halves plus 12. And then performing this product, right? I can see that this is going to be 125 over 8 minus 3 times 25, that's 75 over 4, minus 4 times 5, that's 20 over 2 plus 12. Okay. So now what I'm going to do is I'm going to put them all over 8 so I can perform the additions and subtractions required here. To put the second one over 8, I'm going to have to multiply the top and bottom by 2. To get this one over 8, I'm going to have to multiply the top and bottom by 4. To get this one over 8, I'm going to multiply the top and bottom. In this case, this is 12. I can see it as 12 over 1, right? Okay. So 75 over 4 times 2 over 2. 2 times 75 is 150, okay? And 4 times 2 is 8, okay? Now let me show you how I did that. 75 times 2. 2 times 5 is 10. I carry the 1. 2 times 7 is 14. Plus 1 is 15. Okay? So I don't want you to think for a moment that you want to do these mentally at all. I want you to do your work on paper, because when you do the work on paper, you become better and better at doing calculations, at getting comfortable doing calculations, especially, unfortunately, like long calculations. And that enables you to be more confident when you're handling problems that get more and more involved. Now, 4 times 20, that's 80. Because, yeah, let's do that here. 4 times 0 is 0. 4 times 2 is 8. Right? So this is 80 over 8. And then finally, the 12 times 8. Let's do it here. Oops. 8 times 2 is 16. I bring down my 6, I carry my 1. 8 times 1 is 8, plus 1 is 9. So that's 96. So the 12 over 1, when I multiply the top and bottom by 8, I'm going to get 96 over 8. So I can rewrite this line as 125 over 8 minus 150 over 8 minus 80 over 8 plus 96 over 8. Okay? I can now write this as follows. I can write it as 125 minus 150 minus 80 plus 96. Okay? Okay. So what's 125 minus 150? That will actually be negative 25. Okay? So why is this the case? 125 minus 150. What is that? Well, I can see that as 125 plus negative 150. Okay? Looking at it as an addition of two numbers with opposite signs, I can see that the negative 150 having absolute value 150, the 125 having absolute value 125, the negative 150 has the larger absolute value. And since it has the larger absolute value, I keep the sign of the one with the larger absolute value. So the result of this is going to be negative. And to figure out what value that's going to be, I take the absolute values of both of them and I subtract the absolute values, the smaller, from the larger. Like this. The 150 minus 125. 0 minus 5, I can't do it. But I can borrow from the 5. That becomes a 4. This becomes a 10. 10 minus 5 is 5. 4 minus 2 is 2. 1 minus 1 is 0. So this is negative 25, like this. So I can now rewrite this expression as negative 25 minus 80 plus 96 over 8. Okay? Okay. So now the question is, what is negative 25 minus 80? So this is going to be rewritten as negative 25 plus the opposite of 80. Okay? So if that's the case, I'm adding two numbers with the same sign. So I keep the sign, the result will be negative, and I add the absolute values. What's 80 plus 25? 80 plus 25 is going to be 0 plus 5 is 5, 8 plus 2 is 10. So it's negative 105. Okay? So I can now rewrite this as negative 105 plus 96 over 8. So now the question becomes, what is that? Negative 105 plus 96 is going to equal, I'm adding two numbers of opposite sign. So to find out the sign of the sum, I need to find out which one of these has the bigger absolute value. The absolute value of the negative 105 is 105. The absolute value of the 96 is 96. The negative 105 has the larger absolute value. So the result of this sum will be negative. And the actual value we will get by subtracting the absolute values, the smaller from the larger. The absolute value of the 105 is 105. The absolute value of the 96 is 96. And the 96 is the smaller absolute value. So I'm subtracting 96 from 105. I ask myself, what can I take away 6 from 5? Unfortunately, I cannot. So I would borrow from the 0, but I can't. So I'm going to borrow from this one. This will become a 0. This will become a 9. And this will become a 10. 15 minus 6 is 9. 9 minus 9 is 0. So it's 9. So the result here is negative 9. And we can see that this gives us negative 9 over 8. Okay? So it's a little under the negative 9. It's a little under negative 8 over 8, which would be negative 1. So it's a little lower than negative 1. Okay? Now I'm wondering, when I was doing this table, I noticed, look at, between negative 1 and 0, it's both 12. So what happens in between? Well, so I can figure out by calculating what happens at negative 1/2. So what is f of negative 1/2? Well, it'll be negative 1/2 cubed minus 3 times negative 1/2 squared minus 4 times negative 1/2 plus 12. Okay? So the first thing I'm going to calculate is negative 1/2 squared. That's going to be negative 1/2 times negative 1/2. Because it's going to be 2 copies of negative 1/2 being multiplied. Now if we have a negative times a negative, the result is going to be positive. Right? And so here I'm going to have 1 times 1 is 1. 2 times 2 is 4. So it's going to be 1/4 for the square. And then what I'm going to do is I'm going to figure out the negative 1/2 cubed, because I'm also going to need that. You can tell that that's going to be negative 1/2 times negative 1/2 times negative 1/2, right? We can see that this product is 1/4 because I just did it here. So this will be the same thing as 1/4 times negative 1/2, right? Now we have a positive times a negative. That's a negative. And 1 times 1 is 1 for the numerator. 4 times 2 is 8 for the denominator. So I get negative 1/8. Okay? And I can already calculate what is 4 times negative 1/2. 4 times negative 1/2 is going to be the same thing as, first of all, I need to rewrite the 4 as a fraction. So it'll be 4 over 1 times negative 1/2. Now I have a positive times a negative. So the result will be negative. And I get 4 times 1 is 4. 1 times 2 is 8. It's 2, I'm sorry. And so I get that fraction. So now I can rewrite this line as follows. Negative 1/2 cubed we saw from here that that's negative 1 over 8. We saw from this part, the negative 1/2 squared is 1/4. So if I do 3 times that, it's going to be, so 3 times negative 1/2 squared is equal to 3 over 1 times, what is the negative 1/2 squared? It was 1/4. So it'll be 1/4. By the way, this is, I know this is getting a little bit cluttered here, but this is what you can imagine that you want to have on your scratch paper. 3 times 1 is 3. 1 times 4 is 4. And so what I want you to see when I'm doing this is I want you to see how to carry out a more lengthy calculation. 4 times negative 1/2 is this. So now I have minus from here, and then this one's negative, so it'll be negative 4 over 2. Then finally I bring down the plus 12. And I can rewrite this as negative 1 over 8 minus 3/4 plus 4/2 plus 12. Okay? So now what I want to do is I want to perform this calculation, but in order to do so, I need to put them all in the same denominator. In this case, I'm going to select the denominator to be 8. So I'm going to have to multiply the top and bottom of this one by 2, the top and bottom of this one by 4, and if I see the 12 as 12 over 1, the top and the bottom by 8. In this case, I'm going to see, okay, negative 1 over 8 minus 3 times 2 is 6, 4 times 2 is 8, plus, I'm going to multiply the top and bottom here by 4. 4 times 4 is 16, 4 times 2 is 8, and then I know that 8 times 12 is 96. How do I know that? Because we just did it, right? And that's going to be divided by 1 times 8, which is 8. So now I can set this all over the same bar. Negative 1 minus 6 plus 16 plus 96. And why? Because they're all being added or subtracted with the same denominator. So I can add the numerators and keep the denominator. I can see that here, negative 1 minus 6, that's negative 7 plus 16 plus 96 over 8. Then, what is negative 7 plus 6? That's going to be 9 plus 96 over 8. What is that? That's 96 plus 9. That's 105 over 8. Okay, and that's my value in between here. So 105 over 8. And that's approximately, let me see here. If you think about 8 times 10, that's 80. 80 plus about 20. 80 plus 24 is 104. So that would be like 13. So this is like nearly 13, okay? And we could do the long division to verify that. Let's do that real quickly. Okay, we don't have to, but we're going to do it here just for fun, just for kicks, so to speak. So 8 goes into 105. 8 goes into 10 once. 1 times 8 is 8. 10 minus 8 is 2. I bring down my 5. 8 goes into 25 3 times. Why? Because 3 times 8 is 24. And then 5 minus 4 is 1. 2 minus 2 is 0. And so in fact, the 105 over 8 is 13 and 1 over 8. Okay? So it's a little over 13. And so now finally, after making our table, together with all the facts that we had, so after making our table, and after, by the way, I apologize for the soundtrack. I shouldn't apologize for it because it's absolutely beautiful. It's the sound of rain and thunder. I only hope that you enjoy this orchestral score put onto us by nature at this time. But in any case, let us finish this moment with the culmination of all this work, and that is the beautiful graph that we have set out to draw. And again, we're going to plot it from negative 3 to 4 more or less on the x. And on the y, we're going to have to go all the way up to like 13 or so. So let's do that here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is going to be the 12, and that's going to be the 13, right? So it's 13. 1, 2, 1, 2. -2, -1, 1, 2, let's say 3, and then let's say -3. And now we can start plotting. -3, -30, it's going to be way too far down. -2, 0, here. -1, 12, it's going to go right there. -1/2, above 13, more or less. So about right there. At 0, it's going to be 12 again. So right there. At 1, it's 6. 1, 2, 3, 4, 5, 6. So about right there. At 2, it's again 0. At 2.5, it's -9/8. So it's just under 1, right? So like just like maybe right here. At 3, y value is 0, like this. And we can see that the graph is going to look like this, okay? Yes. And of course, if you wanted to, like if you made this table and you made all these data, then your instructor would know you nailed it. But if you wanted to just be a little bit sure, my advice is that you can label the points. Like you could label this one A, this one B, C, D, let's say E, F, G, and then you could put the table listing what they are. In our case, we already made our table. So let me get rid of this part here, and I could label them. The -2, 0, that's the A, right? You could make a table. In other words, putting the names of your points so that your teacher can compare them. The B is -1, 12. So that's this one, right? You know, you can see what I'm doing. I'm making a beautiful table here. It's unfortunate that I squeezed that in there. The reason why I squeezed that in there is that when I saw this behavior, that they were both equal on either side, I wanted to see what happened in the inside to kind of get a feel for how they were. So that's my C. My D is my point at 0, which of course is my Y-intercept in this case. At 1, I have 6. I labeled that one E. My F is this one, and then my G is this one. So in fact, let's relabel that one as H, and we'll relabel this one as G. So this point here would be our G, and this one would be our H. And so by doing this, you tell your instructor, I know exactly what I was doing. These are exactly the points on the graph. And of course, you know, when you present a graph like this, you can have a lot of confidence that your graph captures the essential properties of the function, of the function's graph. In any case, I hope you've enjoyed this example, and I look forward to seeing you again soon. Thank you so much.